Thank you for staying until the last talk. I know it's late and it's hard to stay awake, but the good news is after the talk everybody gets a free drink. So I hear the words cosmological simulations, and this is going to be talk about cosmological simulations. I'm going to tell you about very exciting new efforts to model formation of young star clusters directly in the cosmological galaxy formation framework. And this is a work with graduate student Hui Li at the University of Michigan. He's doing most of the simulations. The star clusters fit very nicely in the topic of the conference. They're at the intersection of local star formation scales and global dynamical scales in the galaxy. So this is really the connection between large scales and small scales, and it's very important, I think, to understand their formation. What we know about them is that the fraction of all stars that form in active star-forming galaxies becomes larger and larger in the form of massive star clusters as the intensity of star formation increases. And specifically, this plot shows the density of star formation rate, and this is a fraction of all young stars that are formed in the form of star clusters, and there's a very clear trend that this increases for clusters of various age of less than 10 million years and greater than 10 million years. There is a very important and fundamental property of young star clusters, and that's their mass function. So not the initial mass function of stars, the IMI observation that we heard of, but the number of clusters of a given mass in the whole galaxy. That mass function is extremely universal. It's one of the most universally measured properties of any astronomical systems. It can be described by a truncated power law, and the slope of the power law is very well constrained. It's about -2. There is some truncation mass here, but the slope is very steady. It does not vary with the galaxy. There are several examples of regions inside our galaxy and in nearby star-forming galaxies, interacting galaxies, star-bursting galaxies. They all have the same mass function of their young star clusters. So on the right you see a plot from the simulations that I'll tell you about, which show different runs with different efficiency of star formation on very small scales. This is the intrinsic property of how cosmological simulations model star formation. Also different intensity of stellar feedback from those young stars. And in most cases, the resulting mass function is very similar to power law with a similar truncation, with the exception of perhaps one model that we tried, and that is when the star formation efficiency was extremely high. That was taken to be 100% within the dynamical time, and that produces very strong truncation in the mass function. Basically what happens in that case, the feedback is so strong, star formation rate is so condensed, and the feedback is so strong that it blows out the nascent molecular clouds in which the star clusters form, and big clusters just don't have the time to assemble. In all other cases, there is a fairly robust prediction for the mass function, with some variation at low masses, but this is a very good result, and this is the same slope as we see in observations. The simulations are done with the adaptive mesh refinement called ART, which includes a big collaborative project, which includes a lot of the physical processes that we think are important now for modeling galaxy formation and star formation. There is a new prescription, new modeling added for subgrid scale turbulence. If you want to know more details about this, please ask me afterwards at the bar somewhere. I'll focus on the results. We see that the shape of the mass function of these young star clusters is universal in simulations as well. These are results within the same galaxy at different times, just the normalization goes up, but the mass function stays similar. These are results for different galaxies at the same time, and again, except for the normalization, they show the same shape of the mass function. There is some robust result that the mass function does look like a truncated parallel. And this may be that emerging phenomenon that we talked about at the very beginning of this conference. So what is the origin of the shape of this mass function? What happens with it? What you see on the left plot are maximum masses of star clusters that we measure in galaxies at different times, and there's very strong correlation with star formation rate. So the higher the star formation rate, the more massive clusters form in the galaxy, and that sort of makes sense. But if there was no truncation, if the mass function was a strict parallel with no cutoff, then for this given star formation rate, this would be the prediction for the maximum cluster mass that you would form, which you can calculate analytically if you know the star formation rate. And the masses that we see in the simulations are an order of magnitude or more below that value. So this is an indication that there is a real cutoff in the mass function. It's not just a statistical effect, it's not a sampling effect. And the cutoff mass, if we feed the Schechter function, the cutoff mass here also scales with the star formation rate. And we can take a simple relation, just check for consistency. Is the Schechter function a good description of the true shape of the cluster mass function? And if we feed this cutoff mass with a simple relation, that's going to star formation rate scaling as a power of 1.6, and then we can recalculate for that function what is the maximum mass of the clusters we expect, and this is given by this solid line. And the black points are what we actually measure in the simulation. So there's very good agreement, which is a consistency check that this truncated parallel really is the correct and robust description of the shape of the mass function. But where does the parallel come from? So what is so magical about this number of 2? It turns out that it's very different from the PDF of gas cells, which is shown by the line here. It is different from the PDF of molecular gas. In the simulations, we trace the chemistry of molecular formation. We can see what is the mass of actual molecular clouds, not just the dense gas cloud. That mass function is also very different. We form the star clusters within the fixed physical region, which is a sphere of diameter of 10 parsecs, which is meant to represent the typical size of clumps of molecular clouds within which in the local universe star clusters really form. And it turns out that including this fixed physical size changes the slope of the mass function, makes it shallower, and it leads to this dashed line. And then there's a final step that goes from dashed to the solid line, and that is accounting for how star clusters are forming their mass within the few million years that they have that they do it. In the simulation, we have time steps of the order of 1,000 years, and star clusters form on time scales of several million years. So we resolve in time the formation of each stellar particle with thousands of time steps, and we can see how their star formation rate increases and decreases as the result of feedback of their own young stars that they produce. So the final masses that we calculate for star clusters in the simulations are produced self-consistently by the feedback of their own stars. So in that sense, they're true interesting masses to compare with observations. They're not just a result of numerical artifacts or numerical prescriptions as is typically used in galaxy formation simulations. And including the behavior of the star formation rate, which declines over time in the course of a few million years, we get the final shape like this, which is similar to the slope of -2. The blue line is the actual mass function of star cluster that we see. So it's not a trivial way of how this mass function comes about. These are the time scales over which star clusters form. And it's not for each cluster, it's too hard to output star formation histories for each individual particle, but this is a combination, cumulative distribution for all star clusters at a given epoch in a given galaxy that we form. And here the 50% line shows that for these sets of models, half of the clusters will form within 8 to 10 million years. But that is not really the good measure. This is from when the very first star appears in the star cluster until the very last star appears. And the star formation rate declines. So a better measure of the actual duration of star formation is here on the right-hand side. And this is a mass-weighted measure of that duration. This is what would be interpreted as spread of ages in a star cluster as it were observed in the real universe. And the spread of ages is significantly less. I killed it. Okay, I killed it, I can get it back. Okay, here it is. So it's significantly shorter than this duration, and it lasts a few million years. And even if you go to above 50%, majority of the clusters, for most of the models, is between 2 and 4 million years. This is exactly what we observe for the age spread of stars in most nearby young star clusters. With the exception of that one model I mentioned, this red one, which has 100% efficiency of star formation. Here, all the stars form within 1 million years, vast majority. And then their feedback is so strong, they blow out their microclouds and big clusters just don't form. For other models, it's in this normal range. And there is a systematic trend. As you decrease efficiency of star formation, or as you decrease efficiency of stellar feedback, then this duration of star formation increases systematically. So the more concentrated, the more efficient star formation, the faster star clusters form, but you lose in the maximum mass that you can reach. This is what the galaxies look like at two different times. We form disks. They're very narrow, normal, gravitationally supported disks. Here you see the plot of the projected gas density. But the disks are not axisymmetric. There are a lot of disturbances. There are very strong spiral arms. There are satellites being formed. There are a lot of merger of new gas. So the disks are disturbed. There's a lot of turbulence. This new modeling of subgrid turbulence also helps to calculate the feedback more correctly. So there's an interesting question: does this merging effect affects the shape of this mass function or the creation of massive star clusters? Do galaxy mergers promote formation of massive star clusters or not? And I think it's an interesting question. And we've done a bunch of models, very simple analytical models before, showing that if you just make this assumption that in mergers of gas-rich galaxies you form massive star clusters that will become global clusters, then you can produce the mass and metallicity distribution of global clusters in many galaxies, spirals, and ellipticals with the color and metallicity mass distribution similar to what's observed. Here are examples for the galaxies in the Virgo cluster. This was a hypothesis, and it's just interesting to check, do simulations support this idea? Is there any evidence for gas-rich galaxy mergers promoting formation of clusters, which here in the simulations we can do? And there's a lot of arguments why it's a good idea. To form very massive clusters, you need to have very massive molecular clouds. And just to assemble those molecular clouds is much easier when you have a lot of gas inflow and also higher pressure environment which you produce during these mergers. So it sort of makes sense, but does it happen in detail or not? And if we trust the simulations, then there's also the following. The answer is maybe. We see some correspondence. This plot shows star formation split in the galaxy split in two parts. In the gray, it's formation in all stellar particles less massive than 50,000 solar masses. And those are still star clusters, but they're not going to become global clusters. They will be disrupted by their own dynamical evolution in 10 billion years. In the blue, there are clusters with masses above 50,000 that have a chance of becoming global clusters at the present time. And in red, these are durations of gas-rich mergers than this galaxy experience in the simulation. There is not much correspondence early on, and this is only a simulation at fairly high redshift. It only goes to about 3.4 for technical reasons, so we're talking about high redshift. But since the mass function of clusters is so universal in the local universe, we have hope that at high redshift it's the same thing in our comparison makes sense. So there's not much correspondence at high redshifts, but later on, when the star formation gets closer to the peak that the galaxy is expected to have, a lot of massive clusters are forming during this gas-rich merger. We also see that the shape of the mass function is systematically flatter and more power law-like during the merger than between mergers, which is shown by this plot. This red line is a scatter for different times, different realization during merger versus the gray line where it decreases. It's not a dramatic effect, but there's definitely more truncation of maximum cluster mass between mergers and higher cluster masses that we form in mergers. So there is at least some tentative evidence that mergers do promote formation of massive star clusters. And finally, about the efficiency of star formation, the plot I started with, the fraction of young stars forming in the form of massive star clusters. All I showed you before, the observed range, is shown by this purple diagram, and the points are different galaxies that we get in the simulation, and we do have a similar trend. So that does match up. So let me finish with this. We have to take any questions and answer them here or later in the bar. Thank you.
Okay. We have some questions first there. Thank you.
Could I have a question? Yeah. Okay, so in the case of massive star clusters and multiple sequences, there is always so-called mass budget problem, which needs to have very massive, much more massive clusters at some stage, and then they lose quite a high fraction of stars during the evolution. Are you getting some very massive clusters in your simulations? I mean, much more massive than let's say, global clusters.
So all the masses I was talking about are the initial masses at the time when the cluster forms. So you can imagine different scenarios for evolution afterwards. But the masses are here. Here's the here are the mass functions. We get to 10 to the 7 solar masses, and this is even a redshift of 3.3. There's all the lower redshift of redshift 3 or 2 when we get at least this high mass. So this is 10 million solar masses.
So let's say current global clusters can have masses below 10 to 6, so there is some mass also.
But this is 10 times more than the current global cluster masses.
Alec, how does depend your mass function on the feedback prescription? I mean, you are including, for example, radiation pressure, are you including photoionization, or does this mass function change as you change the feedback in the simulation?
Right. So there isn't very strong dependence. There is some, but it's only at lower masses. There is a case. The cyan line has the strongest feedback, and the purple line has a lower feedback, and the green line has even lower feedback. So there's a systematic trend here. The slope changes of low masses, but it's fairly robust at masses above 10 to the 5. So whatever is going to become global clusters, I think is well converged. For low mass clusters, there is dependence.
But this is only a thermal feedback, or it's also included gravity.
So this is a feedback that includes energy of supernovae going into turbulent energy, and it's not immediately decayed, so it's a part of the kinetic feedback. We also vary the efficiency of star formation that affects the number of massive stars, which is radiative feedback.
Just these big clumps, these massive clusters could be associated with the clumps that are observed at high regions in spiral galaxies. I think they are much more massive than 10%.
So I think clumps appear when you do not have very good spatial resolution. When you see on scales below 100 parsec, there is fragmentation. There is fragmentation all the way down. What we see in simulations, this looks like a clumpy structure, but this is 4 kiloparsecs. This is 100 parsecs. This is 100 parsecs. And yes, there is clumping. There are strong spiral arms, but there are no distinct clumps that are not part of the disk. This is still a disk. It's not axisymmetric, but it's still a disk. So I don't think there are any clumps of billion solar masses. 10 to the 7 is the maximum. Okay, for the Milky Way size galaxy, I should have said, this is the size of our galaxy. If you consider a much more massive galaxy, then this will scale up.
Any further questions? No? Okay. Then we have now, but don't go